we will introduce confidence intervals in this video. Let theta be a population parameter and let x1, x2, x3 all the way up to xn be a random sample. Suppose theta check is a point estimator for the parameter theta. Now, if we are given sample data a small x1 through xn and denote this set by x, there's a typo here, not x bar, then the point estimate is going to be denoted by theta check of x for theta. We might want to ask the following question. What is the probability that the point estimator takes the true value of the population parameter theta? That is, we want to calculate the probability that the random variable theta check takes the value theta. Now, notice that if theta check has a continuous distribution, then the probability that it's going to take a fixed value is always going to be zero. This is not good. This means that the point estimate theta x is very precise. We have the value uh, theta check of x as a good value, yet we lack the confidence or the assurance that this point estimate is actually going to take on the value of the parameter theta. A possible solution would be to instead report an interval estimator, right? That is, we want to report that theta lies inside some interval that has the lower bound given by Lx and an upper bound given by Ux. And this interval has to be calculated from the random sample capital X. A consequence of reporting an interval estimator is that we will lose the precision that is involved in reporting an exact estimate, whereas we gain confidence in our assertion that data will actually lie inside the given interval. Note that given a random sample X containing the random variables x1 through xn, L of x is the lower confidence interval bound and U of x is the upper confidence bound. Let's work out an example to get a grounding of what's happening here. So suppose our parameter of interest is the population mean and our random sample x has the random variables x1, x2, x3 and x4. So this is a random sample coming from a normal distribution with mean mu and variance 1. Mu is a constant that we want to estimate and we assume that we know the variance to be 1. In this case, the sample mean defined by the sum of the random variables divided by the sample size, which is 4, is an unbiased estimator for mu. We ask the following question. What is the probability that mu lies inside the random interval given by x bar minus 1 comma x bar plus 1? This is the same as writing out a probability equation that probability mu belongs to the closed interval x bar minus 1 comma x bar plus 1. The central limit theorem tells us that the sample mean is normally distributed with mean mu and variance sigma squared over n. And in this case, x bar is going to be normally distributed with mean mu and variance 1 over 4. As a result, we notice that we have the following standard normal random variable that is given by x bar minus mu divided by the square root of sigma squared over n, which is going to be equal to x bar minus mu divided by half. We now calculate the probability that mu lies inside the closed interval x bar minus 1 comma x bar plus 1. The calculation proceeds as follows. We first note that x bar minus 1 less than equal to mu less than equal to x bar plus 1 is the same as minus x bar minus 1 less than minus mu less than 1 minus x bar. And we follow this with a bunch of elementary arithmetic here, which involves inequalities. Therefore, equation star now gives us that the probability that mu lies inside the closed interval x bar minus 1 comma x bar plus 1 to be equal to the probability that minus 2 is less than equal to x bar minus mu divided by half less than equal to 2. We notice that the last equation is actually a probability involving the standard normal table, so and can be calculated to be 0.9544. This says that there is 95% chance that the random interval x bar minus 1 comma x bar plus 1 contains the population parameter mu. Note that while the probability that x bar equals mu is 0, that is, we have a precise point estimate but zero confidence, whereas the probability that mu lies inside the random interval x bar minus 1 comma x bar plus 1 is 0.9544, which is giving us reduced precision because we are working with an interval here, however much higher confidence. There are a few things we need to note here. The first being that x bar is the random quantity in the probability equation at hand. That is, probability of x bar minus 1 less than equal to mu less than equal to x bar plus 1 has to be equal to 0.95. Secondly, the population variance is known in this setting, right? So that is, we're assuming that sigma square equals 1. Finally, the given sample data x1, x2, x3, and x4, the sample mean is given by x1 plus x2 plus x3 plus x4 divided by 4. And when we report this interval estimate, we will be saying that the population mean mu belongs to small x bar minus 1 comma x bar plus 1 with 95% confidence. This is the same as saying that if we repeatedly sample the population and compute the intervals x bar minus 1 comma x bar plus 1 for each of the sample data, then 95% of the intervals will contain the true population mean, that is mu. We revisit the example. So suppose now our sample data is given as follows. Coming from the normal distribution, we can calculate the sample mean as 5.125. Then with 95% confidence, we can say that the population mean mu is going to lie inside the confidence interval 5.125 minus 1 comma 5.125 plus 1. That is given by 4.125 comma 6.125. Also, if we worked with another sample given by 7.1 comma 4.1 comma 6.1 comma 8.1, we can calculate the sample mean to be 6.55. And with 95% confidence, in this case, we can assert that the population mean is going to lie inside 6.55 minus 1 comma 6.55 plus 1. That is, the confidence interval in this case is going to be 5.55 comma 7.55. Note that the true mean in this case was actually 5.1, and we see that it does belong to the first confidence interval, but not to the second confidence interval given by 5.55 comma 7.55. Also, notice that the second sample was quite unlikely. If we were doing a random sample from a normal distribution with mean 5.1 and variance 1. We now move to understanding 1 minus alpha times 100% confidence intervals for the sample mean. The assumptions are that alpha lies inside the interval 0, 1, and 1 minus alpha times 100 denotes the confidence level. The random sample x is a collection of random variables x1, x2, x3, which are identical and independently distributed, coming from the normal distribution with parameters mu and sigma squared. So mu is the parameter that we're trying to estimate, and we're going to assume that the variance sigma squared is known. The central limit theorem tells us that the sample mean is normally distributed with mean mu and variance sigma squared over n. And we want to solve the following probability equation. Notice that z alpha over 2 is the critical value corresponding to alpha over 2. Pictorially, we are looking for the area under the curve between negative z alpha over 2 to z alpha over 2. We work through the following calculation. Noticing that mu minus x bar over sigma over square root of n will have to lie between negative z alpha over 2 and positive z alpha over 2. And following through with this calculation gives us that mu will lie between x bar minus z alpha over 2 times sigma over square root of n and x bar plus z alpha over 2 times sigma over square root of n. Therefore, the probability equation in 1 uh, comes down to calculating the following probability, which is to say that the probability that mu belongs to the random interval x bar minus z alpha over 2 times sigma over square root of n, comma, x bar plus z alpha over 2 times sigma over square root of n to be equal to 1 minus alpha. The random interval x bar minus z alpha over 2 times sigma over square root of n, comma, x bar plus z alpha over 2 times sigma over square root of n is called the 1 minus alpha times 100% confidence interval for the sample mean when sampling from a normal distribution under the assumption that the variance is known, and it provides an interval estimate for the population parameter mu that is unknown and we would like to estimate. Just to tie this back with the example that we worked out earlier, the population distribution in that context was normal with mu and standard deviation 1, sigma squared, the variance was 1, z alpha over 2 is equal to 2, and alpha was 0.05. This is all for now. Just to quickly recap, we worked through calculating the confidence interval when we are working with a single mean. We will talk more about confidence intervals in later videos. Take care and see you around.